p73, determine whether the following series converge or diverge. We really only have a couple of tools in our arsenal here. Tools in arsenal. I guess that doesn't really make sense, but you get the idea. We can try to determine if we're dealing with an nth term situation, a geometric or arithmetic series kind of deal, and then we'll go from there. All right, so determine whether the following series converge or diverge. It's very, very vague in the way that it's expressed. So most people start with the nth term test, so that's what we'll do. So I'm going to see if the limit as n approaches infinity of 2n plus 3 over 3n minus 5 gives a value that's equal to 0 or dne. All right, those are the only cases. I'm sorry, not equal to 0 or dne. All right, basically you're really kind of looking to see if it's equal to 0, because if it's equal to 0, that's the inconclusive case. If it's something other than 0, then you're probably looking at something that diverges. All right, so let's take a look. So I'm looking at two exponents that are the same. All right, if I plug in infinity, then I can see that it's indeterminate. So infinity over infinity. So we would probably want to apply L'Hopital's rule, unless you're using the horizontal asymptote shortcut, which would be just to take the ratio of the leading coefficients. But just so I can hit that concept of L'Hopital's rule again, LHR, that tells us if we're dealing with an indeterminate case, we find the derivative of the top. Oop, that's not large enough. Derivative of the top, and separately find the derivative of the bottom. All right, not quotient rule, two separate instances of computing the derivative. The derivative of 2n plus 3 with respect to n is 2. The derivative of 3n minus 5 with respect to n is 3. And the limit of a constant is a constant. So 2/3. So the limit as n approaches infinity of 2n plus 3 over 3n minus 5 is not equal to 0 and not equal to dne. Therefore, we're looking at a case that diverges. All right, so we have the divergent situation. Now we can verify it. Let's take a look at the picture. In the right mode. So we want to be in parametric mode. And we want to go with the sum. Because the sequence might converge on a particular number, but it's a question of whether the partial sums will converge on a number. So 2, just, it's in terms of n on paper, but we're doing it in terms of t on the calculator. There's a learning curve there. So 3t minus 5. All right, so starting with 1, going to some really large value of t, dependent on what we call t up here. Our expression, 2t plus 3 over 3t minus 5. Go into the table. It looks like, if we're just kind of going down the line here, it looks like it's getting larger and larger until it kicks over to decimal form. Then it becomes obvious that it's getting larger and larger, never settling in on a particular value. All right, so as the x values corresponding with t increase, the y values corresponding with the summation also increase. All right, and again, just to get it back to the original setting, second window, 0 is our default table start, or what we want our default table start to be. delta table should be 1. When you go back into the graph, that's what it looks like. Now, if you look at the graph itself, you can do a zoom 6, and you see this. I mean, it does a connected graph, even though we told it to make a dot graph. Sometimes that happens, and we just kind of live with it. But each one of these kind of corners here represents a point. All right, and it's just the calculator sometimes has a hard time with it. All right, let me see. Yeah, there's really nothing we can do about that as far as I know. Now, looking at this factorial case, the idea is, again, maybe we can apply the nth term test. Maybe it's something else, but we've got to somehow kind of write this in a form that's a little bit more palatable. All right, so let's just talk about what a factorial means for a second. N factorial can be thought of as n times n minus 1 times n minus 2 and so on, all the way down. Well, it would really be down to a 1, because if you think about, for example, 3 factorial, it's 3 times 2 times 1. It's 1 less every time. All right, so how do we represent going down to a 1, the complete disappearance of an n? We could say that it's n minus 2, n minus 3, n minus 4. When would it get to the end of the line here? We could say n minus n plus 1. All right, so when we get to that nth term, we're subtracting that nth term from the n. That gets you to a 0 plus 1 would give you a 1. All right, so that's one way to look at it. All right, and in fact, that's going to be a pretty useful way of looking at it. We won't always have to go, we hardly ever have to go all the way down to the last term of the sequence, but we will have to evaluate the first couple of terms. All right. Now, that is not always going to be a necessity, because if there's no factorial in the problem, then it won't be relevant, but it's just something to keep in mind. All right, so looking at this one, I'll try the nth term test. Limit as n approaches infinity of n factorial over 2n factorial plus 1. All right, so let's expand a little bit and see what's going on here. All right, so this would be the same as saying the limit as n approaches infinity of n times n minus 1 times n minus 2 and so on, and I'll just do a dot 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 over 2 times n times, I'll just write it as 2n times n minus 1 times n minus 2 dot dot dot, and then at the end of the line here, you'd have a plus 1. All right, so what's going to happen here? Well, you can see here that in both cases, we have a common n minus 1 that can cancel, n minus 2 that can cancel, and everything after that would cancel. So really, this would simplify down if we're just looking at the first term, because we're really just kind of looking at this as finding the n behavior or using the horizontal asymptote rules. If I find the n behavior model, I'm only concerned with the first term top and bottom anyway, so I can ignore that plus 1. All right, so this will help us get the n behavior model. Might remember that from Calc 1. All right, that n behavior model, again, is just the term with the highest exponent on the top of a fraction term, well, among other things. But in this case, it applies that it would be the term with the highest exponent on the top of the fraction divided by the term with the highest exponent on the bottom of the fraction. So when you do that, all this stuff cancels out, and you're left with just an n over 2n, which simplifies to the limit as n approaches infinity of the constant 1/2, which would just be 1/2. All right, that limit
as n approaches infinity of n factorial over 2n factorial plus 1 is not equal to 0 or dne, so it's another case where it diverges. All right.
And so just to kind of hit that point home a little bit, the end behavior, or at least related to the end behavior model, I'll just do a quick example of that just because I know some people need a refresher. If you have something like the limit as x approaches infinity of 2x plus 1 over x squared minus 2. What you would do is, again, just identify the term on the top of the fraction with the highest power, the term on the top of the bottom of the fraction with the highest power, and divide the two. That's the end behavior model. Poor quality arrow here. Let me just do a better job there. So it's 2x over x squared. Which is 2 over x. 2 over infinity would go to 0. All right, so it's just a quick refresher. And the reason why that works, let me just go back into function mode, is because rational functions behave the same way as their end behavior models for large values of x. So here's my rational function. Here's my end behavior model. All right, I'll make one of them bold. All right, and I'll just do a quick zoom 6. All right, so you can see here that if you're looking at the non-bolded ones, in fact, let me just turn off the bold one. All right, you see, as you work out towards the large values of x, or negatively large values, quote unquote negatively large, it appears to be approaching 0. All right, that's useful. But now let's take a look at the end behavior model. You see, toward or around the y-axis, they behave very, very differently from one another. All right, it doesn't have this little extra wiggle in the middle. But as you get to the more extreme values of x, they start behaving just like one another. All right, and so that's the idea behind an end behavior model. All right, you could do the same thing with the factorials. It's just sometimes the calculator has a hard time with that representation because it's in effect a numerical calculator, but it's worth trying. So math probability option 4 brings up a factorial symbol. So 2x math probability option 4, and then the plus 1. And I'll just do a quick zoom 6. See, it's kind of a mess. I'd love it if it were a mess. It's nothing. All right, go into the table, you see very, very small values. All right, looking at those very, very small values as it gets smaller and smaller, it's pretty easy to see that it's approaching 1/2. All right, but in terms of my calculator, it's not showing anything. You know, I'll bring it back to 0 and 1 for my setup. At 0, I should have a 1/3. At 1, I should have a 1/3, then 2/5, and so on. But it's not giving me anything because the calculator is just having a disaster of a time trying to evaluate this. All right. So, I mean, you can try to bring it in closer. Sometimes it does a little bit more. But, yeah, see, it gave us a point, a couple of points. It's trying. Well, actually, this one's not even a point. That one's a tick mark on the y-axis. This one's a little point. It's trying, but it's not doing a good job. All right. So you can try it with Desmos. So y equals fraction. We have x factorial, just an exclamation point for factorial, plus 1. And just get a good window here, hit the home button. Now you can see a little bit, I mean, obviously something more meaningful, and a little crazy on this side, but as you get to larger and larger values of x, you can see that it's the sequence itself is closing in on the value 0.5. For the technology, as you can see, but now we're at the point where you kind of want to start picking and choosing under what circumstances you use the TI and what circumstances you use Desmos. Just bearing in mind, the policies that I allow for don't always translate to other courses, other teachers. So just be mindful of that. We want to have the analytic approaches down, but we can use the technology to support our work there. All right, so looking at C, I see here that I have a difference in my numerator, so I'm going to write this as two separate summations before I even get started, because I have 3 to the nth over 3 to the nth minus 2 over 3 to the nth. All right, 3 to the nth over 3 to the nth goes to 1, so that's nice. All right, now the sum of a sum. All right, so this is weird. The sum of a sum is equal to the sum of the sums. So basically it's saying that I can find the sum of each of these two elements or arguments individually. So it's the sum of 1 minus the sum of 2/3 raised to the nth power. All right. Now, if you think back to the geometric cases that we did before, we had to investigate and determine what the appropriate A value should be by expanding out and all that good stuff. But we only did that because they gave us the sequence, the individual sequence, and not the list of partial sums. That was different. All right, but the list of the elements in the sequence was given to us, so it sort of dictated what the A sub 1 value should be. All right, here we can assume an A sub 1 of 1. All right, so we can evaluate this piece and see that it's going to converge. All right, which is wonderful. All right, and that's because the R value, the absolute R, is less than 1. That's great. It's geometric series test, which we abbreviate with a GST. GST for geometric series test. I've experienced that most people allow for abbreviations when it comes to this stuff, but I've also experienced that teachers often have their own peculiarities. So you might run into one that says, "No, I want you to write out the whole thing." There aren't too many people that don't know what you're talking about when you say GST. All right. So this piece. Well, it's just the number 1. All right. So if I list, there's a couple of ways you could evaluate this, but if we want to prove convergence or divergence, I need to have a justification. All right. So if I want to go the partial sum route, the first value would be 1. All right. The second value, I'd have a 1 and a 1, which would give me a 2 and a 3 and a 4 and a 5. So the nth sum would be ever larger based off of the position within the sequence. All right. If you just wanted to list out let's say A sub n is equal to 1, then the sequence would be 1, 1, 1, 1, da 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 till the end of time. Now, if you add all these up, you're going to get something infinite. All right, so that's wonderful, but how do we justify this? Well, let's take it in a different direction here. So I'm going to just kind of chuck that down there. I'm going to rewrite this. And the method that I'm going to use to rewrite it, let's see, is it on this page still? No, it's on the previous page, is this method, A sub 1 plus dn, because it is linear. All right. So no matter how unfamiliar this may look, this is the equation of a linear function. All right, it's just using a sub 1 instead of the y value of a point on the graph.
If you think about the point slope form of a line, y equals,
I like the a, h, and k notation.
a times x minus h plus k.
You know, some people might know it as y equals m times x minus x sub 1 plus y sub 1, whatever method you like.
This takes on the role of the k plus a times x minus h. All right, h and k is a point on the line.
All right. So if I'm given,
And I'll just kind of sneak it in over here. I'll just kind of write it below. If I'm given the sum from n equals 1 to infinity of just the number 1, I could have the first entry, second, third, and you can go all the way up to the nth, but they're all going to be 1s. So I'm going to have a slope, an a value, quote unquote a value of 0.
because there's no change,
All right. So the a value is equal to 0.
and then I would just need an ordered pair along the way.
All right. So I'll take this ordered pair because position would give me the n value,
While the result, you know, whatever you get as the answer, if you will, would give me the k value. So h and k.
all right. So h and k would be 1, 1. I think I might have said the n value. What I meant to say was the h value. Apologies for that. All right. So, and I'm going to shrink this down. And by the way, this is a long way for me to say that it's going to diverge by the arithmetic series test, but I just want to have a good justification for you. So I would rewrite this as the sum from n equals 1 to infinity of 1 plus 0 times x minus 1. N minus 1.
All right. So this is a way of representing
This series as
an arithmetic series. All right, we could verify it. Plug in a 1, what do you get? A 1. Plug in a 2, what do you get? A 1. Plug in a 3, what do you get? A 1.
and so on. So this shows
That what we're dealing with is an arithmetic series. Now it's a question of, okay, well, will that converge? The arithmetic series converges if and only if a sub 1 and d are both equal to 0. Well, a sub 1 is equal to 1, so it's all over.
All right. So, undo. Undo. Let's try this a different way. Jeez. Why will it not? Oh, there we go. So I'm going to get rid of this because it doesn't look as nice as the other one. So we will say, and I have all this room over here, so I don't know why I'm forcing it into this little tiny space. So this diverges by the alternating series test.
Geez.
We'll get there. Arithmetic series test.
I had it in my mind that we wouldn't call this the AST because the AST is reserved for the what we'll learn to be known as the alternating series. So I just kind of got in my own way.
So diverges by the alternating,
I almost said it again. Diverges by the arithmetic series test
because A sub 1 and D are, oh, well, A sub 1 is not equal to 0.
Really, you don't need them both to. Well, you need them both to be equal to 0 in order for it to be convergent. You don't need them both to be non-zero in order for it to be divergent. You just need one of them to be non-zero. All right.
So if one part of this diverges, then the whole thing diverges. So therefore, the sum from n equals 1 to infinity of 3 to the nth minus 2 over 3 to the nth diverges. All right, and you'll see here that I did not apply a limit in any way. All right, I used different tests. You know, in the first case, I used
a limit, the nth term test, and applied L'Hopital's rule along the way. For the second one, I used the nth term test, and we did some algebra and some knowledge of factorials. And in this case, we just went by tests that we either knew or referred to.
All right. So the last part, or the last little section here, a series such as what you see there is called telescoping because it collapses to one term or a few terms. If it collapses to a finite sum, then it converges by the telescoping series test. All right. So let's take a look at what this boils down to. All right. So we'll start with an expansion. So we'll plug in a 1. So 1 over 2 times 1 plus 1 minus 1 over 2 times 1 plus 3. All right, so that's what you get when you plug in a 1. Now let's plug in something else. Let's plug in a 2. 1 over 2 times 2 plus 1 minus 1 over 2 times 2 plus 3. Okay. And let's just kind of leave it there for a sec.
We'll do more with it in a minute, but let's just see where this
is going to bring us. So 1 over 2 plus 1 is 3, so 1/3, minus 1 over 2 plus 3 is 5, plus 1 over 4 plus 1 is 5, minus 1 over 4 plus 3 is 7. Okay, so we have two opposites that can cancel.
So it kind of begs the question, is this going to be an ongoing thing?
Or is this just a, just a coincidence? All right, so let me continue. I'll save my ... for a minute. We'll go one more.
And kind of confirm in our minds that this is
a thing that's going to continue. So we got to plug in a 3 now. So 1 over 2 times 3 plus 1 minus 1 over 2 times 3 plus 3. All right, so that's giving us 1 over 7 minus 1 over 9. All right, so another cancellation.
All right. So if we had just stopped at this point, then if I were to say, what is the sum of the first three terms of the partial sum, or what is the first 3 terms of the sequence, or what is the sum of the first 3 terms? A bunch of different questions that could be asked. I could be looking at this as a way of making that a shortcut. All right? But then I want to be thinking, okay, well, if I get all the way down to the end of the line,
the very last term would be the nth term, but prior to that,
we'd have the n minus 1 term.
So plus, I guess I'm changing up my dot, 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 making it a little bit more compact.
So if I replace
The n's with an n minus 1, so I want to go one short of the last term. So 2 times n minus 1 plus 1 minus 1 over 2 times n minus 1 plus 3.
Then I can get to the last term, which is just going to be
the expression that's written in the summation. And so shrinky dink, coming right up. So we would be looking at 1 over, so plus 1 over 2n plus 1 minus 1 over 2n plus 3.
all right. So we know that consecutive values seem to be canceling along the way, but let's see what's happening towards the end of the line symbolically.
All right. So if I distribute the 2 here, I'm going to get 2n minus 2 plus 1, which is 2n minus 1. If I distribute the 2 here, I'm going to get 2n minus 2 plus 3, which is 2n plus 1. So this fraction, the 1 over 2n plus 1, would cancel with this fraction, 1 over 2n plus 1. All right, so we have a cancellation here. It's logical to assume that the progression, if it's happening
To consecutive terms in the beginning of the sequence and consecutive terms towards the end of the sequence, that it's going to happen to consecutive terms along the way,
leaving us with just the first and the last term.
So it's really a matter of saying that this whole thing simplifies down when we bring it down to the end of the line.
It's going to simplify down to 1/3 minus 1 over 2n plus 3.
An avenue that we can follow or use to determine what the actual sum is of this series.
Because if we can get out to the n value
approaching infinity,
then
we'll know what the sum of this series is.
all right, so that's what we're going to do. We're going to find the limit as n approaches infinity of this. All right, so the limit of the constant part, get a thicker marker or highlighter, is going to be constant. So that's 1/3 minus the limit. Well, if I plug in an infinity
For n in the bottom of the fractions,
1 over infinity is going to go to 0. So the sum of this series is actually going to be 1/3. So this converges. So we're not always able to determine
what the converging value is, but in this case we can. And that's only because the telescoping series collapses down to just the first and the last term. All right. If we want, we can go back into parametric mode, type in this telescoping series. So 1 over 2n plus 1. So 2t plus 1 is what I'm going to write. Minus another fraction, alpha y equals 1 over 2t plus 3. and you go into your table and see where it's going in terms of the y. So you go on down the line, and it's like, I don't know where this is going until it goes over to decimal form, in which case it becomes clear that it's in the low 0.3s. Seems to be closing in on 0.33-ish. All right. So the 140th partial sum is 0.3298. The 150th partial sum, we're over 0.33. It's just a question of, are we going to keep going? I don't know. So let's go to table set. Let's make this 0 and let's go by hundreds. And watch the calculator go absolutely nuts. No, it's fine. You don't, I mean, if you go higher than 100, you're going to ask for trouble. You see, even now it's kind of going a little crazy with the computation. But you can see it's still presenting you with the answers. It's just taking a little longer to get there. But it does seem to be living in that 1/3 region, right? So the sum of the, and remember, when we go into parametric mode on this, that's what we're getting. We're getting the sum of the series. It's going to be 1/3. All right? So that's kind of a nice outcome.